Okay, I hope everyone had their lunch. Yes, because you will need the energy for the upcoming hands-on sessions. We want you all focused and ready to rumble. So, in the last hands-on session, we looked at how to get indexes and extents, and these can later on be used to access your data. Obviously, you have to map your data domain into your thread indexes, the index domain, and this is something that we will cover now. Mehmet will now present.
Hello everyone. This is the second section of Alpaca hackathon. Sorry. Yeah, I'm going to show how we can parallelly fill a buffer, a space in memory using a grid of threads. And this will also, in this slide, I'm showing how this can be done in an Alpaca code or with Alpaca. If we go over the Alpaca program steps, initially an accelerator is selected. Depending on your backend NX, selecting accelerator is necessary actually. Then device corresponding to the accelerator is retrieved by Alpaca, and there's an Alpaca function to get a device from the concept of accelerator. For example, for Lumi, since it is an AMD GPU, we are going to use HIP accelerator. And from the accelerator, getting a device is the next step. Then at step 3, we allocate memories at the ACC device and the host device. You can see that there's an allocate ubuff host. A memory is allocated in the host in the CPU, and its address is ubuff host, and we allocate buffer in the ACC or ACC device in the GPU, and but the pointer of the address of allocated memory is a variable in our host code. I mean, okay, the memory is allocated at the device, but it is just a number for us in our code. It's just a pointer. And then, of course, we determine the work division. And for determining work division, we need to give the whole grid size so that the work division can be generated by Alpaca. I mean, the block sizes can be found by Alpaca. And then we are going to execute. As you see, allocation and execution of the ACC buffer and execution of the kernel is done at the GPU, for example, AMD GPU for Lumi. And the other operations are done at the CPU. And we execute the kernel. The kernel is expected to fill a buffer in the GPU. Then the buffer will be copied from GPU to the CPU. Yeah, this is what we are going to do actually. Why being copied? Of course, the destination will be the address, the memory address we have already created in the host, because we have allocated a safe region in the memory, and we need to copy from the data we filled parallelly in a fast manner to the buffer at host. Okay. Yeah, there are some very basic definitions I need to go over. Yeah, in Alpaca we initially define the number of dimensions, which will be number of dimensions of data buffers. And of course, this can also be used as a dimensions for the grid size in the work division, but yeah, dimensions is defined as a type in Alpaca. This is actually two. It's a long way of saying two actually. And then we define extents, namely the size of the buffer to be filled. It will be a 2D buffer, as you can see. And yeah, buffer size is extent here. We are allocating a buffer at the host. Buffer size is extent. What is the size of extent? 64 plus 2, 66 by 66. Yeah, the extent is 66 by 66, and the size of the buffers are equal to extent defined. And then we are going to run the kernel using again exec function of Alpaca. These are the basic definitions. But accessing, okay, we have allocated a memory at the host, and we are going to we also created allocated memory at the ACC, but we need to pass this address that we allocated to the kernel, so that kernel will use ubuff ACC address to fill the data in the GPU. Therefore, we need to pass this pointer to the kernel. Okay, we are using here as a kernel argument in execution, but passing only the pointer is not enough. Again, I'm going to show you the longer way, and it's not enough. We need some more information about the allocated memory. Let me show you. Yeah, let's assume that we have 2D data with 15 rows and 7 columns, and data size is an eccentric data size, which is 3, and this is the data that we want to use. Let's assume that. And if we have created a 1D buffer in the memory, it is going to be saved linearly as a single array, but we have created a 2D buffer, and 2D buffers are allocated at the memory with a padding. And why? Because the size of the row in the memory should be multiple of a number, which is called pitch, to make access more standard and fast. Therefore, Alpaca is a function to get the pitch, or the real row size of the data in bytes, so that we will know how many padding bytes are added to the memory. And yeah, this is what actually we'd like to say. 2D memory, 2D allocated data is not easily accessible by giving the coordinates, because there is padding. Yeah. So what we need to do, for example, we need to access to the data at the fifth row and the second column, or the sixth row and the third column, we are planning to access to this data in 2D. What we need the row size, which is I call it pitch 0 here, and then we need the data size to reach to that point. Therefore, we need to sum all the rows till arriving to this data, and we need to do this in bytes. For example, assume that we have a pitch 32, and this is we need to move 5 rows, then 2 datas to access here, and this is a normal multiplication and summation, and then we can get the address. Then the address is dereferenced, and data. This is not data pointer actually. Okay, no, this is pointer, and the data pointer showing this address can be calculated. The address can be calculated like this, or a shorter alternative could also be used if pitch 0 is divisible. Pitch 0 is 32, for example, is divisible by pitch 1, which is 3 here. Therefore, we need additional information to access to a data in a 2D buffer. We cannot just say, give me the data at 5, 2, because therefore we have two additional numbers together with pointer to pass to the kernel. And yes, please.
What is the advantage of storing the data like this into a 2D versus something that is more linear, let's say, like matrix? Usually we just store a line.
Could you repeat please the question? That the audience knows about.
What is the advantage of using 2D buffer instead of 1D buffer? In my opinion, it is easier to visualize or to understand from the user point of view. Okay, when we pass it to kernel, we need to do this kind of pointer arithmetic, but on the other hand, for the whole program, it is easier to feed the data with the host buffer. I think.
Maybe a bit different the question. Why do we need this padding format like this?
Okay. Okay, it is.
This question was also already raised in the Zoom chat. I started to answer to it. Okay, first of all, why do we have 2D data and not assume maybe a one-dimensional vector and then split it into two dimensions by our own? This is in principle possible, but it comes with a disadvantage if you create a large one-dimensional vector and then you say, okay, my line is, let's assume 111 bytes long. Then you say modulo 111 to get the line ID. And a modulo operation is a very expensive operation, so it will be very, very slow compared to you use n-dimensional memory directly. And then you have also n-dimensional indices where you directly can access this data, and you have no modulo operation to access your value. So you are faster on that way. The other thing is, why do we have padding at the end? And padding is nothing else. You have your data here. For example, what do we have as example? We have a data size of 3 bytes, and then we have that is 7 values, and these are the real data where you like to do some computing. But for compute architecture, loading one line of these data And if it has then some ugly numbers, like maybe in the end it is something like 27 or bytes or something like that. It's very inefficient to load only 27 bytes, for example. So depending on the architecture, it's much better to load a full 32 byte value, or for CUDA, for example, in global memory, everything should be a multiple of 128 bytes, because CUDA, from the design of the architecture, prefers to have 128 bytes in one load. If you load less, then the engine at the end, I call it engine, driver, whatever, will load 128 bytes and throw away all other bytes. So it's very inefficient. You have more than a factor 2 maybe in loss.
But we could add the padding just at the end.
No.
Because then we wouldn't have to use this rubbish.
Yes, it's possible. It really is then also depending on what you like to do. So assume, for example, this what we are coming to. We are working on a heat equation. So you have a square maybe with your data, and at some point maybe you like to touch only the. What could you go back?
And the neighbors.
The neighbors. Where do I have a mouse? Let's assume you like only to access these data, this row, to communicate it to your neighbor device via MPI or something like that. Then you need to slice out the data, and slicing out is maybe an operation the underlying API, the backend is providing for you, CUDA, HIP, or something like that, and then it is very or much more efficient if it is has a regular structure like that. So here you can easily describe this Alpaca. Okay, I need only the right side of the data, so one row, and the padding can help to optimize the data access. It can help also with caching hits and misses, with fault sharing, if you then really on a level that you do low optimizations, and then this padding can help. And this is nothing we added in Alpaca because that you can tune everything. This is also something, for example, CUDA or HIP is automatically providing for you. If you create in the native APIs two-dimensional memory, you have also line paddings.
Yeah, just for but the padding, I understand it's just why it is like for each line we create, each row we create the padding and not have just the matrix. And then
Each row is now also starting with a aligned address. So assume here for some reason your data need to be aligned to 32 byte, then you have here also the correct alignment in the row.
Okay. Because of the number of rows.
Yes. No, because of the padding. You have then each row is then aligned to 32 byte.
Okay, yeah.
I hope it helped.
Yeah.
Thank you.
What do you think now?
So our aim is filling a buffer. We are passing the accelerator buffer pointer and two other informations to a two-variable vector to the kernel. And there's of course an easier way. Rather than passing pointer and pitch, we can use Alpaca MDSpan, but we will, and it is easy to access with MDSpan, and for multiple dimensional data, using MDSpan is easier, but now for this example, we are going to use this kernel, which takes the buffer at ACC pointer and two additional variables, which are row pitch and column pitch, or the data type. And yeah, there are two additional DXDY variables which are already defined in the code. You don't need to take them into account. And what we are going to do, each thread is going to calculate some value and going to set this value in the buffer. And the buffer Yeah, this is what we are aiming to do. Each thread simply gets the index in the kernel and sets, by some calculation, sets the data with the index in the buffer. And let me explain in a more structured way. Initially, in the kernel, what we are expected to do in the kernel, find the thread index in kernel to be used as index to set to the buffer. And there's a function, and kernel is going to call this function analytical solution, and which calculates actually the first value of a heat at that point. Then we need to calculate the memory address in buffer using these pitch values and this pointer arithmetic actually, and then set the value at the address with the value calculated using this analytical solution function. This function takes the real position, not the indexes, because the grid, each cell in the grid has dx dy position, dx dy core size. Each cell has a size, of course, in the real physical problem. Therefore, this analytical solution takes two inputs. And what you are expected to do here is writing the inside of this get element pointer, which actually calculates the data point in 2D and then returns the address. Then this address the content of this address will be heat point value. And that's all. As you can see, thread index, getting the thread index is not done, and it should be done by you. And this get element pointer function should be written.